I'm Sapin. I work at Mozilla Research on Clickable Servo, which is a new rendering engine. And it's written in Rust. And as we've heard, Rust was released as well, just this Friday. And when you open a file in Rust, the way that the file name is represented in memory is a bit unusual. And I think it's interesting, so I want to talk about that. But we need some background on how to deal with text. Our CPUs mostly know about numbers and don't really know how to deal with text. So we need a convention to represent text with numbers. And of course, there is more than one way to do it. And in the early days, most of these encodings could only support some set of writing systems. So if I wanted to write Japanese, I had to use Japanese encoding, and I could probably not have Korean in the same document. So what can we do about that? Of course, we make a new one that supports everything. And that's exactly what Unicode did when I was 1 year old. And they decided to have 16 bit per character, which allows up to 65,000 and some characters. And I say character here, but it's a bit more complicated than that in Unicode. You have code units, code points, scalar values, grapheme clusters, and gifts, but we'll keep it simple. And even at the time, there was some concern that 16-bit would not be enough. But the Unicode community really wanted to keep it simple and have 16-bit. And they, even in page 2 of the first introduction chapter of the book, because it was a book at the time, they had this diagram that says, here's how much of the space we have used allocated to characters and how much we have left. And they say that sufficient space for foreseeable, they have sufficient space for foreseeable future expansion. Guess what happened? So meanwhile, Unicode got adopted in many systems. And these systems use 2 bytes per character, because that was the thing to do. And at the time, that was really what you call Unicode. But later, Unicode became more than just one encoding, and so now we call that particular encoding with 2 bytes per character UCS2. And meanwhile, some other people didn't really like this business of 2 bytes per character, so they invented a thing called UTF-8. It looks like this. Each character is represented by one of these byte sequences, and the interesting thing is that it's a variable size. So some characters are just 1 byte or up to 6 bytes. And that allows up to 31 bits of space. And in Unicode version 2, they finally realized it's really not going to be enough 16 bits. So they introduced this system called UTF-16, which is really like UTF-2, so much that you don't really have to do anything in your software that uses UTF-2. The idea is that there is a range of values that were not used that we now call lead surrogates, another that we call trail surrogates. And when you have lead followed by a trail, it's a surrogate pair, and together that pair represents a single character. And that mechanism allows us to go up to 1 million and some characters. But the thing is, Unicode version 2 did not allocate any character to these new supplementary characters that are encoded as a pair. And so there was no incentive really to do anything about it. And even if when you do it right, most code doesn't need to do anything about it either. It's only really when you want to run that text or deal with false. And the problem is, what happens when you have a surrogate that's not in a pair? That doesn't really represent anything, but no one really knows what you should do in that case. So in many cases, the answer is nothing happens. You just have that it's not text. So also in Unicode version 2, they generalized the mechanism of having abstract characters assigned to numbers, and that's separated from the way these numbers are encoded into bytes. And there are multiple encodings in Unicode, including UTF-8 to 16. And these other encodings were artificially restricted to encode the same values as UTF-16. So even though UTF-8 can go up to 31 bits, it was restricted to have this same range of values. And in particular, there is this range in the middle that's used for surrogates that cannot be used in Unicode. And so when you have this byte sequence, ill form, it's not a valid character. Let's go back to Rust. This is the actual definition of the string type in the Rust standard library. It contains a vector of 8-bit unsigned integers, so bytes. And that vector is private, so you have to use the APIs to access it, and the API enforces that the content is well-formed in UTF-8. It represents Unicode characters. And that's really good when dealing with international text to do things correctly, so you don't have mojibake or character encoding errors in your programs. But when you talk to the outside world, it's not always so nice. And in particular, in the operating system APIs, any strings like file names, but other stuff as well, is not necessarily valid Unicode. And it depends on the platform. On Unix doesn't really care about encoding, it's just bytes. But on modern systems, it's almost always UTF-8. And on Windows, it was UCS2 once upon a time, and it's now supposed to be UTF-16, but not always. You can still sometimes have a file name on your file system with a surrogate character in it, not a character. We want to write the Rust standard library to be cross-platform, so that when you open a file, you don't have to care about these differences between platforms. How can we do that? And how can we support any kind of file names, for example? So the standard library has this type called OS string that contains any value that the OS can give you or that you can give to it. And again, on Unix, it's just bytes. And on Windows, we could have had a vector of 16-bit integers, which is what happens in the OS APIs. But really, we'd rather have something that's closer to UTF-8 to have cheaper conversions to and from the native string type of Rust. And if we can avoid allocating memory or copying a lot of data, that's also good. So why can't we use UTF-8 for this? When you have normal character, basic character that's on 2 bytes in UTF-16, that's fine to convert in UTF-8. When you have a supplementary character that's encoded as a surrogate pair, that's also fine. The problem is when you have a surrogate that's not in a pair. But again, in the early days of UTF-8, that algorithm is perfectly capable of encoding that values. So what if we did it anyway? And that wouldn't really be UTF-8, so we should give it another name. And someone came up with that name, which I really like. So we call it that. And this is a superset of UTF-8 where you can also have surrogates, but only if they're not in a pair, which means that when you concatenate 2 strings, in case that you would have lead surrogates at the end of the first and a trail at the beginning of the other one, that would form a pair, and we don't want that to happen, so you have to have special case here to transform that into a single supplementary character. And I think this existed before in Scheme 48 and in Racket, but it was a little bit hand-wavy, not properly defined. So I wrote a spec that defines everything explicitly with a proper